Asteroids are far more than simple space rocks. You are about to discover 25 of the most bizarre things scientists have ever found on them, from ingredients for life to the remnants of shattered worlds. This journey will completely reshape your understanding of our solar system's history. How did water end up on a barren asteroid? And what is the true story behind the strange interstellar visitor called Oumuamua? What do you believe is the most incredible secret still hiding in the asteroid belt? The first discovery shatters a fundamental assumption about these dry, rocky bodies. We found water on an asteroid. The presence of water ice in the deep vacuum of space, where temperatures and radiation should have stripped it away billions of years ago, was a genuine shock to scientists. This was not a mere trace, but actual evidence collected by ambitious missions like Japan's Hayabusa 2. This spacecraft did not just fly by, it touched down on the asteroid Ryugu, fired a small projectile to stir up material, and captured samples to bring back to Earth. The analysis revealed minerals that had been altered by water, telling a story of a once wet world, or at least a world that incorporated water-rich materials from the outer solar system. So how did this water survive? The answer may lie within the asteroids themselves. They are not solid monoliths, but often porous rubble-pile objects. Water ice could be sealed away in their shielded interiors, protected from the sun's relentless glare, a frozen time capsule from the solar system's earliest days. This changes everything we thought we knew about the origin of Earth's oceans. The prevailing theory was that comets, those icy wanderers from the distant fringe, delivered our planet's water. But the chemical signature of water on some asteroids is a much closer match to Earth's. This suggests a far more local source, that asteroids themselves could have been the water carriers that seeded our young world, making life itself possible. And this leads to an even more thrilling prospect for the future. If we can find and access these caches of water in space, they become the most valuable resource imaginable. Water can be split into hydrogen and oxygen for rocket fuel, creating cosmic gas stations. It can provide air to breathe and water to drink for astronauts on long voyages. The discovery of water ice transforms asteroids from mere scientific curiosities into the stepping stones for humanity's journey to the stars. But water was only the beginning of the story. Scientists made an even more profound discovery when they cracked open those precious samples from asteroids like Ryugu and its cousin, Bennu. They found the building blocks of life itself, complex organic molecules. These are not signs of living organisms, but rather the fundamental chemical ingredients required for life to start. Among them are amino acids, the very components that link together to form every protein in your body, and even sugars, the energy sources that power biological processes. Finding such delicate compounds on the harsh surface of an asteroid was completely unexpected. It forces us to reconsider the very cradle of life. The question is no longer if the ingredients for life could form in the void of space, but how many of them rained down on a young, sterile Earth. Picture our planet over 4 billion years ago, a molten, violent world slowly cooling. Then, a constant shower of asteroids and comets, each one a delivery truck packed with organic material and water, pelts the surface. This cosmic bombardment may not have brought life itself, but it could have delivered the starter kit, the precise chemical alphabet needed for biology to eventually write its first chapter. This idea, known as panspermia, suggests that life's raw materials are common throughout the cosmos, scattered by asteroids and comets. The implications are staggering. If our own existence stems from such a celestial seeding, then the same process could be happening right now in other star systems, on other worlds. The universe might be far more hospitable to life than we ever dreamed, all because of these ancient, carbon-rich space rocks. The raw materials for life are profound, but the next discovery reveals a hidden history of cosmic violence. On the asteroid Itokawa, a tiny, potato-shaped world visited by the first Hayabusa mission, scientists made a startling find. They detected remnant magnetic fields locked within its dusty grains. This was bizarre because Itokawa is a rubble-pile asteroid, a loose collection of rocks and dust barely held together by its own minuscule gravity. Such a fragile object should not have its own magnetic field. The presence of this ancient magnetism points to a dramatic past. Itokawa was not always this small. The magnetic signature suggests it was once part of a much larger, fully formed planetary body. This parent world would have been large enough to develop a layered structure with a hot, molten metal core churning at its center. It is this liquid metal core acting like a dynamo that generates a global magnetic field. So how did this large planet become the tiny rubble-pile Itokawa? The answer is a catastrophic collision. In the chaotic early solar system, this parent world was likely shattered to pieces in a violent impact with another object. Itokawa is not a primordial rock, but a mere fragment, a pile of debris that slowly coalesced from the ruins of its own destruction. This transforms our understanding of asteroids. They are not just simple leftovers from the solar system's birth, but also the tombstones of entire worlds that formed and were obliterated before the Earth was even finished. Each time we study one, we are reading the ghostly imprint of a planet that died long ago. The ghost of a shattered world is one kind of mystery, but then an object arrived from a place entirely outside our solar system. In 2017, astronomers in Hawaii spotted a visitor unlike any other, a dark, reddish object hurtling past the sun. They named it Oumuamua, which translates to scout from the distant past. Its trajectory was undeniable. It was an interstellar traveler, the first ever confirmed to enter our cosmic neighborhood. But its strange properties immediately defied all expectations. First, there was its shape. Based on the extreme changes in its brightness as it tumbled through space, scientists deduced that Oumuamua was not round but profoundly elongated, shaped less like a space rock and more like a cosmic cigar or a pancake, perhaps 10 times longer than it was wide. Nothing we have ever seen in our own solar system looks quite like that. Then came the real puzzle, its acceleration. As Oumuamua sped away from the sun, its path could not be explained by gravity alone. It was moving faster than it should have been, as if an invisible force was giving it an extra push. This non-gravitational acceleration sent scientists scrambling for an explanation. One natural theory proposed that Oumuamua was a chunk of solid nitrogen ice, much like a wandering iceberg from a distant Pluto-like world. As it passed close to our sun, the intense heat could have caused the nitrogen to vaporize, jetting off its surface and acting like a natural rocket engine, providing the observed push. Others suggested it was a dusty aggregate of particles, a cosmic dust bunny whose lightweight nature allowed sunlight itself to gently push it along. Yet the very strangeness of its properties, its peculiar shape and mysterious acceleration, led some, like astronomer Avi Loeb, to openly speculate about an even more extraordinary possibility, that Oumuamua was not a natural object at all, but a piece of advanced alien technology, perhaps a light sail from another civilization. This idea, while captivating, remains a fringe hypothesis within the scientific community, which largely favors a natural, albeit highly unusual, origin. The true nature of Oumuamua remains an open question, a tantalizing and unresolved mystery. Its brief visit reminds us that the universe is capable of producing wonders that we do not yet understand, and that our solar system is not an isolated island, but part of a much larger and stranger cosmic ocean. While Oumuamua was a fleeting visitor from another star, a much more permanent resident of our own asteroid belt holds a secret just as profound. Deep in space, orbiting between Mars and Jupiter, lies an asteroid named Psyche, and it is unlike any other world we have ever seen. Most asteroids are rocky or icy, but Psyche appears to be made almost entirely of metal, a colossal nugget of nickel and iron roughly the size of Massachusetts. This is not just a lump of space ore, it is the exposed, beating heart of a failed planet. The leading theory is that Psyche is the stripped core of a protoplanet, a world that was on its way to becoming a full-fledged planet like Earth or Mars billions of years ago. But in the violent chaos of the early solar system, it suffered a series of catastrophic collisions that ripped away its rocky mantle and crust, leaving only its metallic innards exposed to the void. We have never been able to study a planetary core directly. The immense heat and pressure at the center of our own Earth make it forever inaccessible. Psyche offers a once-in-a-lifetime opportunity, a journey to the center of a world without having to dig an inch. This is why NASA has launched a dedicated mission, a spacecraft of the same name, to rendezvous with this metallic marvel. What will it find when it arrives? The Psyche spacecraft will not land, but will spend months orbiting the asteroid, mapping its surface and measuring its magnetic field and gravity. Scientists hope to read its surface like a history book, looking for the scars of ancient impacts and evidence of volcanic eruptions that once spewed molten metal across the landscape. Confirming that Psyche is indeed a protoplanet core would revolutionize our understanding of how planets are built. It would be like finding the fossilized skeleton of a dinosaur, giving us a direct look at the inner structure of the building blocks that formed our solar system. This bizarre metal world is a time capsule holding the untold story of planetary birth and destruction. Yet this metallic world of Psyche represents one extreme, while many other asteroids defy our expectations in a completely different way. They are not solid at all. Imagine kicking a rock on Earth only to have your foot sink into a surface with the consistency of a gravel driveway. This is the bizarre reality of rubble-pile asteroids, celestial bodies that are little more than loose collections of boulders, pebbles, and dust, all barely held together by their own minuscule gravity. They are not monolithic stones, but cosmic sandcastles. The OSIRIS-REx mission gave us a front-row seat to this phenomenon when it arrived at the asteroid Bennu. The spacecraft's cameras revealed a world unlike any we had seen up close. Instead of a solid, craggy surface, Bennu was a jumbled heap of debris. Its landscape was littered with rocks and stones of all sizes, so loosely packed that you could almost see the spaces between them. There was no firm ground, only a treacherous, shifting terrain. This discovery created an immediate and dramatic challenge for the mission, which was designed to touch down and collect a sample. How do you land a billion-dollar spacecraft on a surface that might have the structural integrity of a child's ball pit? The mission team had to completely rethink their strategy. They searched for months to find a safe spot, a clearing just the size of a few parking spaces, where the surface material seemed stable enough to not simply swallow the spacecraft whole. When the historic touch-and-go maneuver finally occurred, the spacecraft's arms sank much deeper into the asteroid than anyone had predicted, confirming that Bennu's surface was incredibly soft and porous. The event was so gentle it was more of a cosmic high five than a landing, but it demonstrated that these rubble piles are incredibly fragile, so what holds them together? The force at work is their own incredibly weak gravity. Each individual rock exerts a tiny gravitational pull on its neighbors. It is not much, but in the frictionless environment of space, it is just enough to keep the entire pile from flying apart. This delicate balance means a rubble-pile asteroid can be torn apart by nothing more than the gentle, persistent push of sunlight, a process called the Yarkovsky effect, which can slowly spin the asteroid up until its own gravity can no longer hold it together. These asteroids are not permanent monuments, but temporary assemblages, constantly on the verge of coming apart and reforming. They are the solar system's most fragile time capsules, preserving secrets within their rocky hearts while their surfaces threaten to crumble at the slightest touch. Even the most fragile rubble pile can hold a stunning secret, one that reveals itself in a sudden, violent release. Some asteroids are not the dormant, silent worlds we expect them to be. They erupt. Astronomers call them active asteroids, and they are perhaps the most dynamic and puzzling phenomena in the entire belt. Imagine a standard, rocky asteroid orbiting the Sun for millions of years in utter stillness. Then, without any obvious warning, it transforms. It suddenly sprouts a glowing coma, a hazy atmosphere, and a magnificent, sweeping tail just like a comet. The distinction between the two types of objects, once so clear, suddenly blurs. What could possibly cause a dry rock to behave like an icy snowball? Scientists have uncovered several potential triggers for these celestial fireworks. One of the most straightforward is a direct impact. A smaller space rock, perhaps just a few meters across, could slam into a larger asteroid at tens of thousands of miles per hour. The collision would vaporize rock and dust, blasting a cloud of debris into the vacuum of space. This ejected material, pushed by the gentle but constant pressure of sunlight, then stretches out to form the asteroid's temporary, brilliant tail. Another possible cause is a process called rotational disruption. Some asteroids spin so rapidly that their own weak gravity can no longer hold them together. The centrifugal force literally overpowers their cohesion, and they begin to fly apart. The surface material slides and shifts, and vast amounts of dust and rubble are flung off into space, creating a spectacular, though short-lived display. Perhaps the most intriguing possibility involves hidden ice. Just as we discovered water-altered minerals on Ryugu, an asteroid might contain reservoirs of subsurface ice. If its orbit brings it just a little closer to the Sun, that buried ice could rapidly turn from a solid directly into a gas, a process known as sublimation. The sudden release of this gas would burst through the asteroid's rocky crust, carrying plumes of dark dust with it and forming a classic comet-like tail. This was the suspected cause behind one of the most famous active asteroids, named 322P/2. This object, discovered in 2013, baffled astronomers when it developed a tail over 800,000 miles long. Observations strongly suggested that a pocket of subsurface ice had erupted, proving that water can survive in unexpected places and can dramatically announce its presence. These outbursts are more than just a pretty light show. They are natural experiments revealing the internal composition and structure of asteroids without us ever having to land. Each eruption tells a story of hidden ice, of a violent collision, or of an object spinning itself to pieces. They are a powerful reminder that the solar system is not a static museum, but a living, breathing, and sometimes explosively active system. The chaos of active asteroids reveals a solar system in constant motion, but some of the most intricate dances occur between pairs of space rocks. Binary asteroid systems are a bizarre and common reality, where two distinct asteroids orbit a shared center of gravity, locked in an endless gravitational waltz. A perfect example of this is the Didymos system, which became a household name when NASA deliberately crashed a spacecraft into it. The larger asteroid, Didymos, is about half a mile wide, and it has a tiny moon, Dimorphos, which is only the size of the Great Pyramid of Giza. This smaller rock orbits its parent every 12 hours, a perfect test subject for a groundbreaking experiment. How do such delicate cosmic pairs even form? One leading theory is that when a single asteroid spins too fast, perhaps nudged by the constant pressure of sunlight, its own centrifugal force can literally cause it to shed material. This ejected dust and rubble can then coalesce into a smaller, secondary body, creating a ready-made moon from the parent's own substance. Another possibility is a gentle gravitational encounter, where two independent asteroids pass near each other and one captures the other, though this is considered less likely. Understanding these binary systems is not just an academic curiosity, it is a cornerstone of planetary defense. The DART mission proved this by successfully slamming into Dimorphos to alter its orbit around Didymos. The goal was not to destroy the moonlet, but to give it a small push, a nudge that changed its orbital period. This demonstrated that we could potentially deflect a hazardous asteroid if one were ever found on a collision course with Earth by using a kinetic impactor to slightly change its trajectory. Binary systems offer the perfect laboratory for such tests, as the change in the orbit of the moonlet is easy to measure from Earth, providing clear and immediate data on the effectiveness of the deflection. These dancing pairs of asteroids are more than just celestial curiosities. They are the proving grounds for the technology that might one day save our planet. The gravitational dance between binary asteroids is complex, but some space rocks take this cosmic choreography to an even more incredible level. They host their own moons, creating miniature solar systems in the vast emptiness of the asteroid belt. The first undeniable proof of this arrived in 1993, when the Galileo spacecraft flew past the asteroid Ida. The images it sent back revealed a stunning sight, a tiny moon no bigger than a couple of kilometers across, orbiting its parent. This moon, later named Dactyl, was the very first asteroid moon ever discovered, and it completely reshaped our understanding of these small worlds. How could an object as small and gravitationally weak as Ida possibly capture and hold a satellite? The existence of Dactyl and other asteroid moons points to a violent and chaotic formation process. The leading theory suggests that these miniature systems are often born from colossal impacts. A large collision between two asteroids does not just create a single rubble pile. It can blast a tremendous cloud of debris into space. Within that cloud, smaller fragments can be caught by the gravity of the largest remaining piece, slowly coalescing into a stable orbit around it. It is a scaled-down version of how scientists believe our own moon formed, when a Mars-sized object slammed into the early Earth. Another possibility is that the rapid spin of an asteroid, perhaps accelerated by sunlight over millions of years, can cause it to literally fling off a piece of itself. This ejected material, if it achieves just the right velocity, could enter into orbit rather than flying away entirely, becoming a permanent natural satellite. Since the discovery of Dactyl, astronomers have found moons orbiting dozens of other asteroids, proving that these tiny planetary systems are not rare anomalies. Some asteroids even boast 2 or more moons, creating complex hierarchies of gravity in the deep. This forces us to expand our definition of a planetary system. The universe is filled with these microcosms, where the same fundamental rules of physics that govern planets and their moons are played out on a much smaller, yet equally fascinating scale. The existence of these miniature solar systems prepares us for a discovery that seems to belong in a science fiction novel. Far beyond the main asteroid belt, in the gravitational parking lots near Jupiter, orbit the Trojan asteroids. These are not just more space rocks, they are pristine fossils from the outer solar system, captured by the giant planet's immense gravity and held in stable points ahead of and behind it in its orbit. The Lucy mission, named for the famous fossilized hominid, was sent to study these ancient relics for the first time. One of its targets, an asteroid named Polymel, presented astronomers with a stunning prediction based on its density and composition. The data suggests it might be so rich in carbon that, under the immense pressures of its interior, that carbon could have been compressed into diamond. This is not a solid sphere of glittering gemstone, but a world potentially studded with diamond-rich materials, a cosmic treasure chest forged in the early solar system. The science behind this is as extreme as the result itself. In the chaotic environment where the giant planets were forming, colossal planetary embryos, some the size of Mars, roamed the outer solar system. These protoplanets were large enough to become differentiated, meaning they heated up and separated into layers, with heavy metals sinking to the core and lighter materials forming a mantle and crust. For a carbon-rich body, the mantle could have been composed of compounds that, when subjected to the incredible pressures deep within the object, transform into the crystalline structure of diamond. Then, in the gravitational pinball game of the early solar system, many of these embryonic worlds were shattered. A catastrophic collision could have blown apart a diamond-bearing protoplanet, scattering its precious core fragments across the cosmos. Some of those fragments, captured by Jupiter's gravity, became the Trojan asteroids we see today. The Lucy mission aims to confirm this incredible history. By flying past these asteroids and analyzing their composition, it will read the story written in their reflected light. Finding evidence of these diamond worlds would be a direct glimpse into the most violent and high-pressure processes that built our planetary neighborhood, revealing that the building blocks of our solar system were far more exotic and spectacular than we ever imagined. The universe is a master sculptor, and its chisel is gravity. Far from being simple spheres, asteroids come in a gallery of bizarre and impossible shapes, each one a testament to the unique forces that formed it. One of the most stunning examples is the asteroid Cleopatra, a world so oddly proportioned that astronomers have nicknamed it the dog-bone asteroid. From a distance, it looks exactly like a cosmic treat for a celestial pet, with two large lobes connected by a thick, narrow neck. This strange form is the direct result of its incredibly rapid spin. Cleopatra rotates so fast that its own gravity cannot pull it into a round shape. Instead, the centrifugal force flings material outward at its equator, stretching the asteroid to its breaking point and creating that distinctive dumbbell silhouette. It is a world constantly trying to tear itself apart, held together by the slimmest of gravitational threads. Then there is the asteroid Bennu, which we encountered earlier as a rubble pile. Its shape is no less peculiar, featuring a pronounced equatorial ridge that makes it look like a spinning top or a giant walnut. This ridge is a direct clue to its recent past. Scientists believe that as sunlight gently pushed on Bennu over millions of years, it caused the asteroid to spin faster and faster. This increasing rotation sent loose rocks and boulders sliding from its poles toward its middle, piling up around its waist in a process called rotational acceleration, literally reshaping the world grain by grain. These are not static monuments, they are dynamic bodies, still evolving under the subtle but persistent touch of solar photons. Every strange contour, every unexpected ridge, is a page in the asteroid's personal diary, recording a long history of cosmic nudges and gravitational tugs. The pristine surfaces of newborn asteroids do not last. Floating in the void for billions of years, they are subjected to a constant, invisible sandblasting that slowly but surely changes their very nature. This bizarre process is known as space weathering. Imagine the surface of an asteroid as a fresh, dark layer of volcanic rock. Now, expose it to a relentless hail of the sun's own particles, the solar wind, and a rain of tiny micrometeorites, some no larger than a grain of sand but traveling at hypersonic speeds. This is not a dramatic, catastrophic event, but a slow and subtle transformation that occurs atom by atom. The high-energy impacts from these microscopic particles vaporize tiny patches of the asteroid's surface. This vapor then condenses back onto the surrounding rock, but it does not simply settle back as it was. It forms a thin, glassy coating studded with microscopic beads of pure iron. This nanophase iron is the key to the entire mystery. Its presence fundamentally alters how the surface reflects light, making the asteroid appear redder and darker over millions of years. This creates a profound problem for astronomers trying to understand our solar system from a distance. When we point our telescopes at an asteroid, we are not seeing its true interior composition. We are looking at this weathered, altered skin. A space rock that might be rich in minerals similar to those found on Earth could look, from our vantage point, completely alien and unfamiliar because its surface has been cooked and painted by the harsh environment of space. This is why missions like Hayabusa 2 and OSIRIS-REx were so vital. By bringing back actual samples, scientists could directly compare the weathered exterior material with the pristine stuff sealed within the asteroid. They could hold the evidence of space weathering in their hands and finally begin to calibrate our telescopes to see through the cosmic disguise and understand what these worlds are really made of. The asteroid you see is never quite the asteroid you get. The pristine surface of an asteroid is a cosmic lie, a weathered mask hiding the true secrets within. But sometimes a piece of that interior makes the journey to us, and its arrival can be as important as its contents. In the frozen wilderness of northern Canada, a brilliant fireball tore across the January sky in the year 2000, heralding the fall of the Tagish Lake meteorite. This was no ordinary space rock. It was a time capsule of unparalleled purity, a chunk of a carbon-rich asteroid that had been delivered to our doorstep in near-perfect condition. Its incredible scientific value lies not just in what it contained, but in how it was preserved. Most meteorites are found days, weeks, or even years after their fall, exposed to Earth's air and water, which quickly contaminate their delicate chemistry. The Tagish Lake meteorite, however, fell onto a frozen lake in the depths of a Canadian winter. Locals collected the fragments while they were still frozen, handling them with extreme care to avoid contamination, and kept them in a continuous state of freezing. This icy landing and immediate curation was like a perfect scientific retrieval operation, preserving the meteorite in the same state it was in while drifting through space. When scientists finally analyzed these pristine black stones, they discovered an astonishingly rich and complex cocktail of organic materials. This was not just simple carbon. The Tagish Lake meteorite was found to be packed with a vast array of organic compounds, including an unusually high abundance of what are called insoluble organic matter. Think of this as the cosmic equivalent of coal or tar, a very primitive and complex type of carbon-based material that is incredibly resilient. More remarkably, it also contained the building blocks of that material, soluble organics, which are the more fragile precursors that can eventually evolve into the complex chemistry of life. Finding such a diverse and well-preserved suite of organics was like finding a perfectly preserved ancient recipe book, with not just the final dishes, but all the raw ingredients laid out beside it. This meteorite gives us the clearest picture yet of the chemical factory that was the early solar system. Its pristine nature confirms that asteroids were not merely carrying a few simple amino acids, but were rich in the entire toolkit of prebiotic chemistry. The violent processes of star death and nebula clouds had already done much of the hard work, manufacturing complex organic molecules in the cold dark of interstellar space long before the planets even formed. These compounds were then incorporated into asteroids, which acted as refrigerators, keeping them safe for billions of years. The Tagish Lake meteorite is our direct evidence of this process, a frozen piece of an asteroid that tells us the raw materials for life are not only common out there, but they can survive the journey to worlds like our own, sealed in ice and stone. Even the most seemingly inert asteroid can suddenly come alive. While orbiting the asteroid Bennu, the OSIRIS-REx spacecraft witnessed something no one had ever seen before. The surface of the asteroid was spouting. Dozens of small particles, some the size of marbles, were being ejected from Bennu's surface and launched into the space around it. This was not a one-time event. The spacecraft's cameras caught multiple episodes of this mysterious activity, with particles either briefly orbiting the asteroid like a tiny swarm of bees or slowly drifting away into the void. Here was a world actively shedding its own skin. The immediate question was what force could possibly be powerful enough to lift this material off the surface, given Bennu's incredibly weak gravity. Scientists quickly ruled out impacts from tiny meteoroids, as the frequency and pattern of the ejections did not match what a bombardment would create. The true cause appears to be the asteroid itself, reacting to the harsh environment of space. One of the leading suspects is thermal stress. Think of Bennu as a rock sitting in a cosmic oven, its surface baking in the direct sunlight for hours, then plunging into the deep freeze of shadow during its rapid 4-hour rotation. This constant extreme heating and cooling makes the rocks expand and contract. Over time, this stress can cause fractures. Suddenly, a thermally stressed boulder can crack apart with enough force to fling its fragments away from the surface. Another compelling theory involves the release of water, but not in a way you might expect. Bennu contains water locked within its clay minerals. When the sun heats a water-rich area, the energy can break the water molecules free from their rocky prisons. As this water vapor escapes from the interior, it builds up pressure until it finds a weak point in the porous surface and bursts out in a tiny jet carrying dust and pebbles along with it. This process turns a dormant asteroid into a very slow-motion, leaky geyser. These spouting events are far more than a celestial curiosity. They are a primary force shaping the asteroid's evolution. Every particle that escapes represents a tiny loss of mass, gradually altering Bennu's orbit through a subtle rocket-like effect. The pebbles that fail to escape and fall back to the surface are not landing where they started. They are resurfacing the asteroid, covering old craters and creating new, fresh landscapes. This constant churning means the surface we see is remarkably young, geologically speaking, erased and rewritten by these gentle but persistent outbursts. The asteroid is not a static fossil, it is a dynamic world, still breathing and changing before our eyes. The asteroids we have found tell only a partial story, a collection of planetary crusts and metallic cores. But what about the layers in between? A major puzzle has confounded planetary scientists for decades: the strange and persistent absence of mantle asteroids. If the asteroid belt is truly a collection of shattered protoplanets, then we should be tripping over chunks of their stony mantles, the thick layer that sits between the metallic core and the thin crust. Yet despite all our searching, we have found virtually none. This is the missing mantle problem, a glaring hole in our understanding of the solar system's formation. Where did all the mantle material go? One of the most compelling theories points the finger squarely at Jupiter, the solar system's gravitational bully. This idea is known as the Grand Tack hypothesis. It proposes that in its infancy, Jupiter did not form and stay put. Instead, it embarked on a dramatic migration through the young solar system. According to this model, Jupiter first moved inward toward the Sun, plowing through the region that is now the asteroid belt. Its immense gravity would have acted like a cosmic wrecking ball, violently stirring up the protoplanets that were forming there. The chaos would have been absolute. Many of these budding worlds, with their differentiated layers of core, mantle, and crust, would have been shattered in colossal collisions. But Jupiter's influence did not end there. The theory holds that Saturn's formation then pulled Jupiter back outward, causing it to swing through the asteroid belt a second time. This gravitational double whammy would have been catastrophic for the mantle material. The simulations are clear. This grand orbital dance would have scattered the majority of the asteroids, and particularly the mantle fragments, ejecting them entirely from the solar system into the cold darkness of interstellar space. The few mantle asteroids that might remain would be incredibly rare, hiding in plain sight, their weathered surfaces perhaps masquerading as more common types of space rock. This grand planetary migration not only explains the missing mantle, but also why the asteroid belt today is so sparsely populated, a mere remnant of the incredible mass that once resided there. The belt is not a pristine construction site, but a cleared-out battlefield, and Jupiter's ancient movements may have been the decisive event that determined its barren state, leaving behind only the ghosts of shattered cores and crusts to tell the tale. Far beyond the realm of shattered protoplanets and active asteroids, in the deep freeze of the outer solar system, lies a reservoir of even more ancient material. Out in the Kuiper Belt, a vast disk of icy worlds beyond Neptune, astronomers have discovered objects with a bizarre and telling feature: surfaces of an ultra-red color, darker and redder than anything found in the inner solar system. This is not the simple rust that tints Mars, but something far more complex and primordial. The leading suspect for this strange coloration is a class of complex organic compounds known as tholins. Tholins are not a single substance, but a tarry, complex mixture of molecules formed when simple ices like methane and nitrogen are zapped by ultraviolet radiation from the sun or bombarded by cosmic rays. Think of it as a process of cosmic cooking, where the basic ingredients of ices and simple carbon compounds are slowly baked over billions of years into a thick, reddish-brown organic sludge. This material is some of the most primitive and chemically rich stuff we have ever identified in our solar system. It represents a very advanced stage of prebiotic chemistry, a thick organic soup that formed in the cold, dark reaches of space long before the planets finished assembling. The presence of tholins on these distant worlds is a direct hint at the incredible diversity of ingredients that were available for life's genesis. While asteroids delivered amino acids and sugars to early Earth, these Kuiper belt objects were brewing something even more complex, a heavier, more resilient type of organic matter. Finding these ultra-red surfaces tells us that the outer solar system was not a barren wasteland, but a vast natural chemical laboratory. The processes that created life's building blocks were not rare or special. They were a fundamental part of how our planetary system evolved, operating from the hot inner belt all the way out to this frigid, distant frontier. These distant chemical laboratories are not the only places where ice behaves in strange and dramatic ways. On some of the largest asteroids and dwarf planets, the very ground can erupt. This is cryovolcanism, a process where a world's internal heat melts not rock but ice, creating volcanoes that spew water, ammonia, or slushy mud into the vacuum of space. The most stunning example sits in the heart of the asteroid belt on the dwarf planet Ceres. For years, Ceres was just a faint dot in our telescopes, but when NASA's Dawn spacecraft arrived, it revealed a world of profound mystery. The most captivating of all were the brilliant white spots dazzling from the darkness of the Itokawa crater. These were not reflections, but something actively painting the landscape with a stark, brilliant white. Dawn's data revealed the source. The spots were vast deposits of sodium carbonate, a kind of salt. This was the residue left behind by a cryovolcano. The process begins deep within Ceres. Scientists believe the dwarf planet retains enough internal heat from its formation, and perhaps from the decay of radioactive elements, to maintain a layer of briny water beneath its rocky crust. An impact like the one that created the massive Itokawa crater could have fractured that crust, creating a pathway to the surface. The pressurized, salty water from this subsurface ocean then rushed upward, erupting into the cold vacuum. In the airless environment, the water instantly vaporized, freezing into a fine mist of ice crystals that drifted away, while the heavier, dissolved salts and carbonates settled back down, snowing onto the surface and accumulating into the breathtakingly bright deposits we see today. This was not a one-time event either. The clarity and brightness of the deposits suggest they are remarkably young, geologically speaking, with some formations perhaps only a few million years old. This means that Ceres is not a dead world, but a geologically active one, its frozen heart still beating, its hidden oceans still occasionally finding a way to burst forth and paint its surface with the evidence of its hidden life. Light bouncing off an asteroid carries a hidden message in its very orientation. When sunlight strikes a surface, the reflected light waves can become polarized, meaning they vibrate predominantly in one direction. By measuring this polarization from Earth, scientists gain a powerful remote tool to understand an asteroid's surface without ever touching it. A smooth, solid surface polarizes light in a predictable way, while a rough, porous landscape of fine dust, known as regolith, scatters the light and creates a completely different polarization signature. This is where the puzzles begin. Some asteroids exhibit polarization patterns that are deeply contradictory. An asteroid that, based on its color, should be rocky and solid, might show the polarization signature of an incredibly fine, fluffy powder. It is as if you were looking at a solid marble, but its reflection told you it was made of freshly fallen snow. This bizarre mismatch forces a re-evaluation of the very ground beneath our robotic landers. The leading theory suggests that the surfaces of these asteroids are not simply blankets of sand, but are covered in an extremely porous and fragile layer of microstructures. Imagine a landscape not of grains, but of microscopic fairy castles, a delicate foam of glassy bubbles and fantastically shaped spherules created by eons of space weathering. This intricate microstructure would scatter light in incredibly complex ways, producing the strange polarization we observe. This material, finer than talcum powder and more fragile than a honeycomb, could explain why spacecraft like Hayabusa 2 and OSIRIS-REx sank so deeply upon contact. They were not landing on solid ground, but plunging into a sea of microscopic architecture. Each polarization measurement is a clue, a glimpse into a world where the very dust is engineered by the harsh environment of space, creating a terrain far stranger than we ever dreamed. The asteroid Vesta presents a profound geological contradiction. Data from the Dawn mission revealed something utterly unexpected on this dry, rocky world, evidence that water once flowed across its surface. This was not liquid water as we know it, but a briny slurry that seeped through the rock, leaving behind unmistakable trails of its brief existence. The clues are etched into the sides of craters where Dawn's cameras captured sinuous, branching channels, patterns that could only have been carved by a fluid. How could such a thing happen on an asteroid devoid of any atmosphere and exposed to the vacuum of space? The answer lies in a fleeting, violent sequence of events. When a smaller asteroid slammed into Vesta, the immense energy of the impact did not just blast out a crater, it instantly melted any ice hidden within the subsurface rock. This created a temporary, superheated brine that surged across the scorched landscape. But in the airless void, this watery flow could not last. It either instantly boiled away into space or rapidly froze solid once again, its brief journey preserved forever in the twisted, hardened channels it left behind. This discovery shatters the simple division between wet and dry worlds. It proves that water was a pervasive ingredient, even in the hot, inner regions of the asteroid belt where Vesta formed. The building blocks of the solar system were not segregated into dry rock and pure ice, but were often mixed together. Vesta's story suggests that countless rocky bodies may have harbored these hidden, transient oceans, their water locked away in minerals or as subsurface ice, only to be momentarily liberated by cosmic violence. The water that carved these ancient gullies was a ghost, appearing and vanishing in a geological instant, but its lingering mark forces us to rewrite the early history of our entire planetary system. Jupiter's orbit is not a lonely highway, but a cosmic caravan route. It is escorted by vast swarms of asteroids known as the Trojans, which do not trail behind the planet but are locked into a gravitational dance, leading and trailing it in its path around the Sun. These celestial hitchhikers are held in place at stable points known as Lagrange points, where the gravitational pull of Jupiter and the Sun perfectly balance the orbital motion of the asteroids. It is a delicate equilibrium, a cosmic parking spot where these ancient rocks can ride along for billions of years, utterly stable. The upcoming Lucy mission is designed to be a grand tour of these Trojan swarms, a journey to multiple asteroids that will give us our first close-up look at these primordial fossils. Because they have been held in this stable gravitational embrace for so long, the Trojans are thought to be pristine remnants from the very dawn of our solar system, preserved in the deep freeze of space far from the Sun. They are likely time capsules containing a record of the conditions that existed when the giant planets were still forming. By studying their composition and structure, the Lucy spacecraft will read that record, telling us not just about the asteroids themselves, but about the original ingredients and the violent migrations that shaped the entire planetary system. These aren't just more rocks, they are the untouched building blocks of the outer solar system, and their story is our story. Some asteroids are so dark they swallow the light. These cosmic shadows, often carbon-rich worlds, possess an albedo so low they reflect virtually no sunlight, making them blacker than a lump of charcoal. This extreme darkness is not merely an absence of light, but an active property of their composition. Their surfaces are coated in a thick layer of complex, dark organic molecules and minerals, a tarry residue from the solar system's earliest chemical experiments. This material is so effective at absorbing photons that when you look at one of these asteroids, you are essentially staring into a void, a patch of emptiness where a world should be. This profound blackness creates a cascade of bizarre physical effects. The most immediate is temperature. An object this dark absorbs nearly all the solar energy that hits it, heating up dramatically despite its distance from the sun. Yet in the vacuum of space, this heat has no air to transfer into, so the surface facing the sun can become scorching hot, while the side in shadow remains in the deep freeze of space. This incredible temperature difference creates intense thermal stress across the rock, a constant push and pull that contributes to the fracturing and eventual erosion we see on asteroids like Bennu. For astronomers, these blacker-than-black surfaces are a monumental observational challenge. Trying to determine their size, shape, or rotation rate is like trying to study a shadow dancing in a dark room. They are notoriously difficult to spot and track, often only revealing themselves when they pass directly in front of a distant star, causing a telltale blink in the starlight. Their darkness hides their secrets, forcing us to send spacecraft on daring missions just to illuminate what has been hiding in plain sight all along. That profound blackness creates a vicious cycle of cosmic consequences. On the darkest asteroids, sunlight does not simply bounce off, it is absorbed completely, and that trapped energy holds the power to re-sculpt the asteroid itself. This is the Yorp effect, a bizarre and subtle force named for the 4 scientists who worked out its physics. It is not a sudden shove, but a continuous, gentle pressure that can, over millions of years, literally tear a world apart. The process begins with an asteroid's irregular shape. Imagine a lopsided space rock, shaped roughly like a potato with a large bulge on one side. As it travels through space, sunlight strikes its surface. The bulge absorbs more sunlight than the flatter areas, heating up unevenly. Later, as that heated spot rotates into the cold darkness, it re-radiates that accumulated heat back into space. This release of thermal energy acts like a tiny, natural rocket thruster. Because the bulge is off-center, this minuscule push exerts a torque on the asteroid, ever so slightly altering its rotation. If the geometry is just right, this process can cause the asteroid to spin faster and faster, year after year, millennium after millennium. The consequences of this slow-motion acceleration are dramatic. We have already seen its handiwork on asteroids like Bennu, where materials slid toward the equator, piling up into a distinct ridge and reshaping the entire world. But the Yorp effect can push much further. As the spin rate increases, the centrifugal force growing at the asteroid's equator can eventually overpower its meager gravity. When this happens, the asteroid does not simply crack, it undergoes a gradual disintegration. Loose rocks and dust on its surface are flung into space, and if the spin continues to accelerate, even large boulders can be lifted off and ejected, creating a temporary cloud of debris or even forming a new binary system. This is how a seemingly solid world can be dismantled by nothing more than sunlight. Astronomers have even identified asteroids caught in the act of this Yorp-induced destruction. One such object, known as 2015TB145, was observed spinning so rapidly that it could no longer hold itself together, actively shedding its own material into a faint surrounding cloud. This gentle photonic pressure is a primary architect in the asteroid belt, a silent sculptor that can form ridges, create binary pairs, and ultimately dismantle the very worlds it has shaped, all with the quiet, persistent power of light. The asteroids we have explored are not just made of common rock and metal, they are also mineralogical wonderlands. Scientists are now identifying exotic minerals on these space rocks, substances so rare or unusual they challenge our understanding of how planetary materials form. One of the most widespread and telling of these is a beautiful green mineral called olivine. On Earth, you find olivine in certain volcanic rocks and even as the gemstone peridot, but it is typically buried deep within our planet's mantle. Finding it in abundance on the surfaces of asteroids like Vesta was a genuine surprise. This is a mineral that forms in high-temperature environments, and its presence out in the open tells a clear story. It means we are looking at a piece of a planetary mantle, the deep internal layer of a protoplanet that was shattered long ago, its inner secrets now exposed to the vacuum of space for us to find. But the exotic mineralogy goes far beyond olivine. Some asteroids, particularly the metallic ones, contain minerals that simply do not form under Earth's surface conditions. These are compounds forged in the hearts of doomed protoplanets, where immense pressure and searing heat created stable crystal structures that are impossible to replicate here. Think of the incredible pressures deep within a planetary core, where a swirling ocean of molten nickel and iron slowly cools over millions of years. In that extreme environment, atoms arrange themselves into lattices that are utterly alien to our experience. We sometimes find alloys and intermetallic compounds that have no name because they have no natural counterpart on our world. These exotic minerals are more than just scientific curiosities. They are direct records of the most violent and high-pressure events in the early solar system. Each unique crystal structure is a frozen moment, a snapshot of the conditions inside a world that no longer exists. By cataloging these rare minerals, we are effectively reading the biography of the protoplanetary disk itself, learning about the temperatures, pressures, and cooling rates that were commonplace when the planets were first assembling. This bizarre menagerie of space-borne crystals reveals a history of cosmic alchemy far more dramatic than we ever imagined. Even the most violent scars can be hidden by time and gravity. The Japanese Hayabusa 2 spacecraft revealed this ghostly truth on the asteroid Ryugu, mapping its diamond-shaped surface in incredible detail. As the probe surveyed the terrain, scientists expected to see the usual collection of impact craters, the pockmarked history of any ancient space rock. Yet one enormous depression was conspicuously absent, a crater so large it should have dominated the landscape. The evidence for this ghost crater was not visual but gravitational. By carefully tracking the subtle wobbles in the spacecraft's orbit, the team could map the asteroid's gravitational field, creating an X-ray vision of its interior. There, buried deep within the rubble, they found the telltale signature, a massive circular region of lower density. This was the ghost, the invisible remnant of a cataclysmic impact that had once nearly shattered Ryugu. The reason this colossal crater vanished from view lies in the asteroid's fragile nature. Ryugu is not a solid rock but a loose pile of boulders and dust. When a large object slammed into it, the impact did not carve a permanent bowl into a hard surface. Instead, the entire asteroid flexed and shuddered, its porous interior compressing at the point of impact. Then, over ensuing millennia, Ryugu's incredibly weak gravity took over. The loose rubble, constantly shifting and settling, slowly flowed to fill the depression like sand in an hourglass smoothing itself out. The surface expression of the crater was completely erased, but the internal damage remained, a permanent wound sealed beneath a featureless plain. This discovery fundamentally changes how we interpret the surfaces of rubble-pile asteroids. A smooth, uncratered area does not mean a young surface. It can mean the exact opposite, a landscape so ancient and dynamic that even the largest scars have been healed by gravity's gentle, relentless touch. Every seemingly blank slate on an asteroid could be hiding the ghost of a forgotten cosmic collision. The strangest discoveries force science to ask its most daring questions. To truly grasp the depth of the Oumuamua Mystery, we must venture into the realm of a fringe but fascinating scientific possibility. While most astronomers favor a natural explanation for the interstellar object, a small minority, led by Harvard astronomer Avi Loeb, have put forward a hypothesis so radical it challenges our very place in the cosmos. They suggest that Oumuamua's peculiar properties, its unusual shape and its non-gravitational acceleration, could be explained if it was not a natural rock but a piece of advanced alien technology. The argument hinges on the object's unexpected push away from the Sun. A light sail, a hypothetical form of spacecraft propulsion that uses the gentle pressure of sunlight for thrust, would exhibit exactly this kind of behavior. If Oumuamua was a discarded light sail drifting through the galaxy, its thin, wide structure would account for its strange, flattened shape, and the pressure from starlight itself would provide the extra acceleration that gravity could not explain. This is not the mainstream conclusion, and the vast majority of the scientific community firmly believes a natural origin, like a nitrogen iceberg, is far more likely. But the very fact that such a speculative idea was seriously debated in scientific circles is a testament to how profoundly bizarre Oumuamua truly was. Its anomalous nature was so complete that it pushed researchers to consider every conceivable answer, even those that venture into the territory of ancient, derelict technology from another star. This is the ultimate impact of a truly unexplained discovery. It stretches the imagination and forces us to confront the humbling possibility that we may not be the only builders in the universe. The ghost of Oumuamua continues to drift away, carrying with it an unresolved question. Was it a strangely shaped piece of cosmic driftwood, or the first fragment of a galactic archaeology we are only just beginning to comprehend? From the ghostly imprints of vanished worlds to the faint breath of escaping particles, these 25 discoveries reveal a solar system alive with drama and mystery. Asteroids are not the simple, barren rocks we once imagined, but dynamic worlds, each with its own complex story of violence, survival, and even the delivery of life's essential ingredients. They are the exposed hearts of failed planets, the frozen cradles of organic chemistry, and the active, breathing bodies that continue to shape our cosmic neighborhood. This journey through the bizarre has shown us that our solar system's history is written not just in the planets, but in these countless smaller worlds, each a unique piece of a grand, unfinished puzzle. The next time you gaze at the night sky, remember that the darkness between the stars is not empty. It is filled with these ancient travelers holding secrets we are only beginning to uncover. So keep looking up, follow the daring missions that journey to these distant rocks, and nurture that sense of wonder, for the next great discovery is already out there waiting for us to find.